Bismillahirrahmanirrahim. Assalamu alaikum warahmatullahi wabarakatuh. My dear panels, greetings for the day. Myself, Muhammad Salman Sikandar Badshah. I'm going to present a video presentation on Master Project 1, PS1, on the topic Aerodynamic Characteristics of Sharp-Edged Delta Wing on Rolling and Pitching Motion. My supervisor is Dr. Shabuddin bin Mat. In the slide, I have given some outlines of the topics which I am going to present in this video. The first topic is introduction, which I am going to give the details about the delta wing and some advantages and why we are going to use delta wing. And then the second topic is about the literature review. On the literature review, I am going to I have collected papers, journals, information from the journals of the Sharp-Edged Delta Wing, and the scope of the project, Master Project 1, Master Project 2, and the problem statement and the objectives are under the literature review heading, and the methodology. Under the methodology topic, I'm going to discuss about the methods which I'm going to use in this project under the methodology topic. And the conclusion includes the results which I have got in PS1 and also what I'm going to do on the PS2, which is the Master Project 2. And now we can get into the introduction. Delta wing. Delta wing is in a triangular shape. Because of this triangular shape, the Greek uppercase letter delta, because of the similarity of the shape, the delta name is used as delta wing. And you can see the examples of the pictures of delta wing, and some advantages of the delta wing are listed here. Suitable for high-speed subsonic and supersonic flight because of wave drag is kept down due to low relative thickness, and then due to the action of leading edge vertices, it produces vertex lift, which is advantageous in increasing lift, and also naturally stable in pitching, as horizontal tail surface controls pitch, which is misunderstood as the tailless. But delta wing is considered as blended wing or blended tail. Okay. Right. Why we are going to use delta wing? As you can see, aircraft is a transport vehicle which can travel faster than any So for traveling faster with full efficiency, we need delta wing. And also nowadays we are getting advanced. So still we are in an advanced stage on flying is not a acceptable one for the technology. So the delta wing has an ability to fly on the supersonic speed, and then the ability of maneuvering at high angle of incidence. Delta wing is used, and also we can improve the lift on the high angle of attack. These are some of the delta wings examples. I mean the types of delta wing. Cropped delta wing, which has a tip which is cut off, and the tailed delta wing, which has a tail. Normally delta wings have blended tail. Here the tailed delta wing type has a tail-like structure, and these are the examples, I mean the type of the delta wing. The factors affecting the flow topology over the delta wing is discussed in the slide. As you can see, the sweep angle, which is the sweep of the delta wing, and the angle of attack, the Reynolds number, Mach number, leading edge blunders. These all affect the flow topology. For example, an angle of attack. As the angle of attack increases, the steadiness of the flow decreases. Say why all the factors have the affecting factor on the flow. Now we are going to see about the literature review of sharp edge delta V. So now, as you can see, for the sharp vertex of the sharp edge delta wing, Jadal Haq et al. On 1985 has published a paper, The Discrete Vertices for a Delta Wing. In this paper, he has stated that at an angle of attack, two large vertices is formed because of the separation in leading edge, separation of flow in leading edge. And the shear layer formed because of the flow separation rolls and forms into a primary vertex. Underneath the primary vertex, the primary vertex intensity of the primary vertex increases as it moves downstream. Underneath the primary vertex, there is a secondary vertex which is formed in the opposite direction. In this slide, author Verhanka NG, Kunset VF 2005 published a paper on the flow on the apex of the sharp edge delta wing. They have used oil flow fluid method and Mach number 0.15 and have noted the separation and attached line, and they have sequenced the separation number. Which for the primary separation 1 will be the number, and the secondary separation 2 will be the number. As you can see, the leading edge, the shear flow lines and leaves the wing separation as S1 and rolls up again and attaches in the A1 point, which is the primary vertex. A1 point, which is the primary vertex, and then the secondary vertex, which is formed because underneath the primary vertex, the flow leaves the separation, which is the S2, and then again it attaches in the A2, which forms the secondary vertex. The vertex flow increases along the delta wing leading edge. Again, the sharp vertex of sharp edge delta wing in Kuripa on 2006, accurate physical and numerical modeling of complex vertex phenomena paper is published. In that paper, he has said that at high angle of attack, at high sharp edge delta wing, high sweep sharp edge delta wing, and at high angle of attack, vertical shear layer is formed, which rolls up and forms the primary vertex. The intensity of the primary vertex increases as it moves downwards because of the high pressure gradient between the leading edge and the primary vertex. A secondary vertex is developed which rotates in counter rotation of the primary vertex, and then at small angle of attack, shear layer is formed along the leading edge at which the flow separation takes place for sharp edge ideal delta. In this slide, again, vertex of the sharp edge delta wing is discussed. Author Lurking JM on 2013 published a paper on BFE2 stating that in high swept sharp edge delta wing at an high angle of attack, separation induced which rolls up and forms the primary vertex, which then again reattaches, again separates underneath the primary vertex, which is in counter rotating direction of the primary vertex, which is called the secondary vertex, and at moderate and high angle of attack, vertex induced lift increases largely because of the suction pressure and the vertices and the flow vertices. We are going to talk about vertex breakdown of sharp edge delta wing on the G. As you can see in this experiment, Kolhamen and Wentz has used the Schiller system for flow visualization. In that, lift and pitching characteristics they have noted as 60 to 65 degree delta delta wings has little change in initial breakdown, and 70 to 77.5 degree breakdown depends on sweep degree. The breakdown depends on the sweep degree, and 80 to 85 independent of the sweep degree of the delta wave. And the vortex breakdown is influenced by the pressure gradient, and the vortex breakdown is stable on the apex, and as it moves downstream it becomes unstable, and the vortex breakdown occurs at constant angle for sweep angles greater than 75 degrees. In the slide, the continuation of the vortex breakdown. Um, Author Shahabuddin bin Ether. In this paper, the author has said that the vortex is starting. The vortex of the sharp edge is starting from the apex of the wing to a center of the trailing edge, delta wing. Um, After that point, the unsteady organized flow of the vortex, which is called the vortex breakdown, is formed on the trailing edge of edge area, and um, the flow characteristics vortex breakdown is determined by the Reynolds number, angle of attack, and the leading edge luminance. These experiments are done on smoke with laser with smoke flow visualization. Um, The continuation of the vertex breakdown slide, Lu Shen and Shi Yong Wang on 2018 published a paper on vertex breakdown location. In this, they have mentioned that the vertex breakdown interaction depends on the instability cross flow and instability streamwise. With the flow visualization, smoke flow visualization technique, as you can see the black line, which is the core of the vortex, and here which expands as the vortex breakdown, and after that a wake is formed. With the vortex breakdown, uh, the vortex lift decreases, and the instability of the delta wing also decreases. Here in the slide, continuation of the vertex breakdown on rolling. Author Verhangen NG and Narding SHJ on 1989 published a paper which is shown here. In that, they have conducted an experiment on the biconvex sharp edge delta wing using the flow visualization technique. They have come to a conclusion that asymmetric cross-flow structure gradually alters with side slip due to the change in vortex strength and boundary layer transition, and the vortex breakdown influence the distribution of the surface and the structure of the vortex upstream and the downstream. No vortex is formed behind the trailing edge of the delta. As a continuation of the vortex breakdown on rolling, sharp edge delta wing, author Chatterjee on 1996 have published a paper on numerical roll solution of delta wing, numerical simulation. In that, he has said that vortex breakdown is influenced by the static roll and the dynamic roll characteristics of the sharp edge delta wing, and vortex breakdown dynamic effect is largely controlled by the roll rate induced in the conical chamber. The slow propagation of the vortex breakdown primarily defines the major duration of the circumstances of the roll oscillation. For the vertex breakdown of the sharp edge delta rolling, Vardaki and Gruhal on 2004 published a paper. In that, they have said that they have two cases. One is the static case, and one is the dynamic case. On zero angle, they have no much difference in static case and the dynamic case. Moreover, they have used dive flow visualization technique The digital particle image velocimetry technique on water tunnel study. A coherent vortex is formed at the large roll angles and is observed throughout the roll angles. Throughout coherent vortex is formed and is observed throughout the whole roll angle, and at high roll angle of attack, vortex breakdown formed at the trailing edge may be delayed. As far the dynamic case is concerned, the coherent vortices is formed on both sides with full cycle frequency of small dimensionless, and the amplitude variation becomes small when the rolling motion frequency increases. And for the research of delta wing vortex flow experiment, two has been conducted in 2003, which is established in Europe and USA on 65-degree experiment on 65-degree delta wing configuration, which is of the two main divided to two main facets. One is experimental and another. As you can see the VFE2 profiles, these are the configuration of the delta wing. You can see the sharp edge, which I'm going to experiment in this project, and this is the medium, small radius, and the medium radius, and the large radius. These are the configurations of the delta wing, which is given by the author Hammoldi on 2006, published the paper on VFE2. The slide has the comparison between the blunt and sharp edge of VFE2 configuration. As you can see on the onset, the primary vertex from the apex of the leading edge, and for the medium radius leading edge, onset comes little down as the increasing angle of attack increases. At high angle of attack, in sharp leading edge and the medium leading edge, the surface fluctuation occurs because of the vertex breakdown. Vertex breakdown mainly occurs in the primary vertex. In medium radius leading edge, the primary vertex, which has the highest pressure loss, and strong vertex, which is assisted with the secondary vertex, and also causes additional suction underneath the primary vertex after the formation of the primary vertex. The inner vertex strength is reduced due to the viscous strength, and in the sharp leading edge, the upper surface has the primary vertex is formed, and a secondary vertex, no inner vertex is formed. Comparison of the blunt versus sharp. Author Lurking GM 2014 has published a paper on the 65-degree delta wing sweep, has stated these results, which is in this slide. Has said that the primary vertex of the sharp edge delta wing is fixed on the leading edge, and for the blunt edge it is not fixed, and for the vertex suction pressure reduces in magnitude as it approaches the trailing edge, but in blunt edge, the flow attaches at 20%, and the vertex suction peak occurs at 30% root chord. And then the sharp edge, the wing in the outer primary edge is formed along the leading edge. The primary vertex is formed along the leading edge, but on the blunt edge, it travels towards the trailing edge. Outer primary vertex shift inward due to the leading edge bluntness. As you can see, this chapter, the author has stated these results in his paper. And The VFE2 on sharp edge delta wing. Author Shabuddin bin Mat and al. on 2008 published and paper on this, and they have stated that the shear layers formed, which is the result of flow separation at the leading edge and rolls up and forms the primary vertex. Underneath the primary vertex, due to the pressure gradient, the secondary vertex is formed, and these separation of the primary and attachment of the primary vertexes is determined by the angle of attack and the Reynolds number, and the flow separation system and the flow system, the vertex system over the wing is originates from the wing apex and continues on the trailing edge throughout the flow. In this VFE2 stoppage, the Hamul author on 2013 has published a paper. In this, he has said that vertex breakdown moves upstream as the angle of attack increases. And here in the vertex breakdown on delta wing, as you can see, the experimental installation in the wind tunnel at the downstream of the return, unsteady motion of the vertex is observed, affecting the vertex characteristics determination in the fixed position. And sharp edge vertex, you can see the vertex evolution is affected by the Reynolds number with small values, and the vertex breakdown is observed in spiral type at the downstream. The fluctuation are not concentrated in the core as cited in this paper. As you can see, the problem statement is that the flow in the leading edge of the sharp edge delta wing with the VFE configuration is is not calculated in any of the papers, and the flow is very complicated. So I have decided to data up all the characteristics of the vertex and the rolling condition is limited to 8. In addition to that, there were many investigations were done in VFE2 blend, but not on the sharp edge, so the data is unavailable. So I to give the data for the VFE2 conduct this objective. Main objective of this project is to investigate the experimental nature of the primary vertex and the vertex breakdown and the rolling and pitching experiment of the sharp edge delta wing VFE2 configuration. The scope of this project is as shown in the slides, and the mid-tunnel experiment will be done on VFE2 sharp edge configuration on the MP2 PS2. And these are the Gantt chart of Master Project 1, Master Project 2, and the methodology. As you see, these are the installation in the UTM wind tunnel of VFE2 delta wing, sharp edge delta. This is the pressure tabs to measure the pressure, and this is the sharp edge, leading edge. Here are the pressure tabs, here are the pressure tabs. These are the dimension of the VFE2 leading edge. As you can see, these are the test configuration. Pin configuration: sharp edge delta wing, velocity at 30 meters per second, angle of attack increases 2 degrees each, and yaw angle -20, -10, 0 degree, and 10 degree. The measurement techniques used is here: surface pressure measurement on the wing, flow visualization, tuff technique, and laser experiment. The values of the test configuration has been calculated. For the literature review, the sharp edge delta wing in the VFE2 configuration, as I have no data for the vertex breakdown, and also for the rolling and pitch rolling, and the data during the rolling is also unavailable. The two techniques which I am going to use in the next semester is the surface pressure measurement, tuff technique, and the laser technique. Work to be executed in the next semester, execution of the experiment, data accuracy. Thank you so much for patiently listening my presentation. Thank you so much, panel. Hope I could do this well on the PS2 Master Project 2. Um, uh, Jazakallah khair. Assalamu alaikum wa rahmatullahi wa barakatuh.